All right, today we're going to pull back the curtain on something that's all around us all the time, but totally invisible. It's this wild, chaotic dance of molecules that we feel as temperature. And trust me, once you get what's really going on, it kind of changes how you see, well, everything.
So let's start with a real-world mystery. I'm sure this has happened to you. You wake up, there's that first real chill in the air, you go out to your car, and bam, the tire pressure light is on. You think you have a flat, but you don't. What's going on? It's not a nail, it's just pure physics. And the answer is hiding inside the tire itself.
To figure out this whole tire situation, we need to zoom in. I mean, way in. We have to shrink ourselves down and see the world at a microscopic scale to witness this constant, invisible dance that's happening right under our noses. So here's the fundamental idea, the thing you have to get your head around. Everything, and I mean everything, the air you're breathing, the chair you're sitting on, is made of zillions of tiny particles that are never, ever still. They're always jiggling, vibrating, and bouncing off each other like crazy. So then, what actually is temperature? We see a number on the weather report, but that's not what it is. Temperature is literally a measurement of how fast those tiny particles are moving. It's a speedometer for molecules. When we say something is hot, all we're really saying is its molecules are moving, on average, super, super fast. And this is the whole game right here. Hot just means fast-moving, energetic particles. Cold just means those exact same particles are moving way more slowly. They're more sluggish. That's it. The speed of this invisible dance is what we're actually measuring when we check the temperature. Now, obviously, for science to work, we can't just say things are fast or slow. That's not going to cut it. We need a consistent, reliable way to put a number on all this molecular energy. And that, of course, is where our temperature scales come into play. So you probably know Celsius and Fahrenheit, right? They're super handy for daily life because they're based on something we all understand, water. You've got freezing at 0 or 32, boiling at 100 or 212. But for scientists who really need to measure the energy itself, there's a much more fundamental scale. And that's the Kelvin scale. What makes Kelvin so special is where it starts. It doesn't start at the freezing point of water or anything else for that matter. Its 0 point is the true absolute bottom, the point of zero energy. And this is it. Absolute zero. 0 Kelvin. That's about negative 273 degrees Celsius. This is, theoretically, the coldest anything can possibly get in the entire universe. It's the point where that invisible dance of molecules grinds almost to a complete halt. Almost. Okay, so hotter means faster moving molecules. Got it. But what does that actually do to the stuff they make up? Well, all that microscopic motion has some very big, very visible consequences. Think about it like this. Imagine a really crowded dance floor. If everyone is just standing still, you can pack a lot of people in. But what happens if the DJ puts on a great song and everyone starts dancing like crazy? They're going to need more room, right? They'll push each other apart. Molecules do the exact same thing. The hotter they get, the more they move, and the more space they take up. We call that thermal expansion. And this expansion can happen in a couple of ways. Sometimes it's mostly in one direction, like a long, thin railroad track getting just a tiny bit longer on a hot day. That's linear expansion. Or it can happen in all three dimensions, like the air in a hot air balloon puffing up and getting bigger. That's volume expansion. Okay, let's zero in on gases for a minute. Because with gases, the particles are already super far apart and flying around like tiny little billiard balls. It might look like total chaos, but it turns out that chaos follows some surprisingly simple and predictable rules. So, rule number 1, Boyle's law. This one's pretty intuitive. If you take a bunch of gas and you squeeze it into a smaller box, what happens? Well, those particles are going to slam into the walls of the box way more often. And that's all pressure is, more collisions. So less volume means more pressure. Simple. And here we go. This is Charles's law, and this is the secret to our flat tire. If you heat up a gas, its particles move faster, they push outwards more forcefully, and the whole thing expands. And of course, the opposite is true. If you cool a gas down, it shrinks, it contracts. And that's exactly what's happening on that cold winter morning. The air inside your tires gets cold, it shrinks, and poof, the pressure drops. Mystery solved. Now this one is probably the one you already know without knowing its name. Avogadro's law basically just says that if you add more gas to something, it gets bigger. You blow more air into a balloon, the balloon gets bigger.
More particles need more room. It's as simple as that.
So we've got these different rules, right? One connects pressure and volume, another connects volume and temperature. But what if there was one single powerful equation that could tie them all together? Well, you're in luck. There is.
And there it is, the ideal gas law. It looks simple, but this little equation is incredibly powerful. It's like the master key that shows you how pressure, volume, and temperature are all dancing together, all perfectly linked. Let's break it down real quick. P is pressure, V is volume, N is just how much gas you have, and T is your temperature. And remember, for the math to work, that temperature has to be in Kelvin. That R in the middle, that's just a special number called the gas constant that makes all the units play nicely together. And this is what really makes it all make sense. That P for pressure, it isn't some weird abstract force. It is the real physical result of trillions and trillions of tiny particles constantly slamming into a surface. That's all it is. Okay, but you probably noticed a key word in the name of that law: ideal. The ideal gas law is called that for a reason. It's an amazing model, it gets us super close, but it makes a couple of small assumptions. And in the real world, the rules can sometimes bend a little bit. See, an ideal gas assumes the particles themselves are just tiny points that take up no space, and that they don't have any attraction to each other. But in reality, they do. Real gas particles have a tiny bit of volume, and they have a tiny bit of a weak pull on each other. Now, most of the time this doesn't matter. But if you really squeeze a gas into a tiny space, or you cool it down so the particles are moving really slow, those little details start to become important.
And of course, science has an answer for that. People much smarter than me have come up with even more advanced equations that actually account for the real size of molecules and the little forces between them. This gives them an even more precise picture of how gases work under all kinds of extreme conditions.
So, there you have it. From the air in a tire to the fizz in a soda can, it all comes back to the same thing, this invisible dance of tiny particles. It's happening everywhere, all around you, all the time. Now that you know the basic steps to the dance, the real question is,